Welcome to the course on power quality. Today we will like to discuss improved power quality converters. In that we will discuss AC to DC buck converter. Well, coming to outline of the presentation, we will like to introduce this improved quality buck converter, then we will classify them. We will discuss principle and operation and control of buck improved power quality converters. Then we will talk analysis and design of buck improved power quality converter, modeling, simulation, performance of buck improved power quality converters, followed by some numerical examples which we will summarize, and then have a references at the end of presentation. So, we have of course, the objective of today lecture with the requirement and application of buck improved power quality converters. We will talk configuration of buck improved power quality converter, and we will talk about control of buck improved power quality converter, necessary design of buck improved and method of modeling and control of buck improved power quality converters. So, coming to the buck type of improved power quality converters, they are used for downing the voltage, and of course, it has a less number of component and it offers quite good efficiency, 95% or more even in quite low rating in many of the circuit used, and it has applications of course in switch mode power supply, applying low voltage for processors like starting from 1.8 to 3 with the or without synchronous rectification. We will talk about applications some more little later. The advantage of this buck improved power quality converter is the voltage across the main switch of the buck converter is almost clamped to the input voltage, that is the higher voltage in the circuit. Therefore, the buck power factor correction converter can achieve relatively high efficiency with the universal input voltage range. It provides comparatively low device count, and it has continuous output current. Of course, there are some disadvantages of these buck improved power quality converters. The buck power factor correction converter fails to provide a sinusoidal waveform for the input current at the zero crossing of the input voltage, and there is a strong trade off between power factor and output voltage correction. The input current total harmonic distortion and output voltage ripple becomes higher because of discontinuous current of the smoothing inductor. Therefore, a large smoothing inductor is required. Well, the applications which we are mentioning, there are plenty of applications where we use like lighting system, like normally LED lighting system. You can reduce the voltage to the required level with less number of components. Another major application is coming as a battery charger, which are used very extensively number of applications, including like your typically electric vehicles or the battery chargers for many other applications. Then DC power supplies, because you want to have a regulator supply, then uninterruptible power supply, and computer power supplies, of course, ceiling fan drives, portable hand tools, and home appliances like so these are some of the applications, and of course, you can think about like a typically applications photograph like maybe for lighting system, like either electronic ballast for typically for fluorescent lamp or LED bulb driver. They normally we called the driver because the voltage output of DC, it totally depends on typically on how many LEDs you are connecting in a string in series and parallel, and moreover of course, this converter have a power factor correction on the supply side. Then the other applications may be like a laptop charger, mobile chargers, low power battery chargers, then the uninterruptible power supply, DC power supplies, printer power supply, then fax machine power supply, computer power supply, and ceiling fan driver. So these are some of the applications practically also. Now, we can classify this buck improved power quality converter into many category, like first is the supply based classification, which can be like a typically single phase or 3 phase, or you can have a further classification that whether power flow is unidirectional or bidirectional in single phase as well as in 3 phase. Then structure based classification, you can have like a buck type improved power quality converter either for non isolated configuration or isolated configuration, which further can have a further classification like whether you are using a bridge type structure for the converter into it, or you are using semi bridgeless, or you are using fully bridgeless. These are the concept is coming in your buck converters, and similar concept is for isolated, whether you have bridge or semi bridgeless or fully bridgeless configuration, means virtually you are avoiding the diode bridge rectifier in case of this bridgeless configuration. That is the concept of what I mean. a bridgeless configuration like. Then another aspect is the design and control. So, typically the control also depends up to some extent little bit on the design. Then first improve water quality converter with CCM control, that called continuous conduction mode control. Usually the continuous current or continuous voltage, I mean depends on energy transfer component, like whether you are having energy transfer through inductor. So, then we call it continuous conduction mode, current mode of control. And if you are using a typically the let us say capacitors as energy transfer device in some of the converters, there we call it of course the you can call it continuous conduction mode of voltage across the energy transfer device like. So, if you are designing CCM, of course control differs compared to the another one with buck improve water quality, but DCM control, discontinuous conduction mode, as well as the sensor requirement also changes in that case. So, component value changes in the converter, as well as even the you can call it like sensors requirement also changes in these control. And similarly, buck improved with the critical conduction mode. Critical conduction mode we call it normally a boundary condition control also, that it is in between DCM and CCM. And why we want to operate in this in critical conduction mode, because we want to take advantage of CCM as well as DCM typically in this control like. I mean the benefit of DCM, which of course we will talk about little later also, that your component size is reduced, I mean especially the inductor size is reduced compared to CCM, as well as the sensors are also reduced, but of course stresses on the component increases like. Coming to now single phase unidirectional buck improved power quality converters. So, you have a many configuration of the circuit even in case of single phase, that first you starting like a single phase unidirectional buck converter with your input AC filter. So, we have a EMI filter on the input side, and after the diode rectifier we have a typically the buck converter, I mean which really control the voltage at the output or reduces the voltage, I mean always lower, but you can of course get either the variable voltage or you can get a constant voltage. It totally depends on your typically on application requirement like, I mean also, or the EMI filter, I mean this filter can be on output of diode rectifier. The benefit of keeping a filter at the output of diode rectifier is that the diode can be of now power diode, because the current in the diode rectifier is continuous. In this case, because you are operating normally this switching device at much higher switching frequency. And why we operate this device at much higher switching frequency, because there are benefit that the size of this your filter component or energy storage component, especially the LD and CD can be reduced, especially LD can be reduced, the inductor can be reduced by increasing the switching frequency of the device. But the problem is like then you have to select all these, even diodes also of high frequency if you are taking this configuration. But in this case, because you are putting this your EMI filter or input filter typically after the diode rectifier, so diode rectifier can be now a power diodes, and that are much cheaper than you can call it the diode which you use the high frequency switching diode like. And of course, I have already mentioned that we normally like to use a much higher switching frequency, so that especially the size of the inductor is reduced, and moreover you are able to replace energy very fast across the output across the load like. So, another of course configuration is that you can have typically as even a self commutating component with the diode here and the EMI filter. Of course, then you cannot go with the high switching frequency, and in that case typically I mean like using the GTO or so, but normally can be used in case of your higher you can call it like much higher power rating like. The another configuration can be that after typically this configuration with the soft start, you can have a like isolated buck converter. Isolated buck converter can be like a, because you might be reducing the, in many applications we have a requirement for isolation. Apart from that, your bridge converter provides you the buck operation like in that case. So, buck operation can be one, the fixed buck operation can be because of the transformer turns ratio you can do. Another can be that you can change the duty cycle and reduce the voltage at the output, which are applied the primary to the primary winding of this high frequency transformer like. So, that also another kind of, we will discuss more in detail little later on that, because in many applications we require isolation also. So, coming to like analysis of this single phase unidirectional buck converter, this is a typical first configuration we have talked about with the component, and you can go to the relation for that buck converter in, if you are operating in CCM. So, directly the output DC will be the duty cycle multiplied V in, where the V in you can take the average voltage output of the your diode rectifier, and then you can have a inductor current in the two modes. On mode, this is on period, how the inductor have a voltage input minus output, and when you have a off mode means device is not conducting, then the due to freewheeling action, I mean the inductor certainly will cause the current to flow. So, if you are operating in CCM, of course, after this mode again we will go to this is on interval, but if you are operating the converter in DCM, then after even off interval the current in inductor becomes 0. So, you have a third mode where neither the device is conducting nor the diode is conducting, like. And from these relation, of course, you can have a typically the derivative of the current can be expressed in that form, and for during typically for off period when diode is conducting for continuous conduction, that is the equation. So, where T is the switching period and D is the on duty ratio. From these two equations, the value of the inductor can be estimated, and you can clearly see, I mean the value of the inductor depends on switching frequency. As you increase the switching frequency higher, the value of the inductor can be reduced, and it also depends on current ripple in the inductor. So, if you allow the current ripple more, then the inductor further can be reduced it. And we were just mentioning either boundary condition. Boundary condition means you are allowing the inductor current to go to 0. So, it means in that case further inductor value can be reduced to typically the ripple permitted in that case will be even much higher. So, it means your inductance value can be further reduced, like in that case, like. So, in case of buck improved power quality converter, the average inductor current during the switching cycle is equivalent to the output current, and from that you can find out the considering the eta j ripple in the inductor current, the minimum value of the inductor can be calculated from switching frequency, and the ripple into that ripple percentage ripple, how much you can multiply the output average current in terms of the average, like. So, that is the how you can have for continuous conduction, and for DCM calculation for this inductor for you can call it DCM, we calculate for the critical conduction mode, I mean like typically the expression, and this is the expression typically we can call it for critical conduction mode, I mean like where the ripple will be like a twice of your output current, virtually you are going from 0 to twice to 0, I mean like in that case, and initially you are allowing the current twice. So, that we call it critical, but if you want to operate in for critical, this will be the inductor, but you want to operate in DCM, certainly the inductance will be much lesser than this LD critical, I mean like. So, it means you can reduce the further size of the inductor in case going to be want to go to in DCM, but you can understand, I mean like once your maximum current is going to inductor twice of output current, it means your device rating, the peak current rating of the device will be even more than the twice of the output current. So, that is a kind of penalty, and as far as this in single phase perfector correction converter, I mean this is the same relation for second ripple for capacitor output capacitor calculation, that depends because you are having a second harmonic ripple at the capacitor. So, this is virtually output current divided by your 2 omega delta omega. So, this also depends on how much ripple you are permitting and how much is the load. So, as you increase the output power for a given output voltage, you will find the capacitor required higher, and apart from that even the if you are permitting voltage ripple less, then also capacitor is required higher, like. I mean it depends on application that how much percentage of voltage ripple you can permit it, like in this kind of situation, like. So, that is about the design of these capacitor and inductor value, and coming to the calculation typically for operating power factor, the input current is equal to the on time and average current. So, that is the input current, and you can even talk about this current related to in terms of duty cycle and the input output voltage, that is the current coming from the input, and which can be the average can be similar to this, and the output if we can consider that this will be proportional to this if voltage is output voltage low. So, this voltage term is quite high compared to that, and then you can define the power factor in terms of this, which can be of course from power you can derive the relation for RMS current, and finally the power factor can be related in terms of your duty cycle, where the alpha is duty cycle, of course it becomes reasonably nonlinear function, and where the maximum value of duty cycle can be your V output upon V 1, which is considered here, like I mean also. So, we consider that you can easily get a with power control the power factor correction like also, but of course in DCM you get inherent power factor correction compared to that. So, coming to like a bidirectional, that these were the unidirectional in the sense many applications we require unidirectional power flow, all the power supply applications which we mentioned like LED lighting, we have a unidirectional power flow, but some application we have a bidirectional power flow also. So, where of course, we have a much different configuration in buck converter. So, here we are using a virtually, you can think about after the filter a current source inverter, the current source converter you can call it, which is interface typically here. And the interesting part is here, we want here the current can be sinusoidal in phase with the voltage, so that you can get unity power factor, but the current here will be like a PWM current, only then you can control the current here on the input. And when you have a PWM current, you can just see, it means you are going to have a current from 0 to the current corresponding to the DC link current, which is here like typically, or it can be like a part of your load current like which are flowing in the inductor. So, this current will be a segment of the output current. So, when it is any diagonal switches are on, this current will be a function of this input current, and when you want to make it off 0 current here, then you have a freewheeling action that you have to switch on both the devices of same lag. This is interesting features here, and that will give you a freewheeling action. So, output current cannot be changed quickly because you have inductive filter, but here the current will become 0 because current is not coming virtually from the input circuit like So, in this case you can have either power flow this way or this way in this, that is the reason we call it bidirectional power flow. However, the current direction can be opposite to with the voltage, but the voltage at the output cannot change the polarity. Output voltage will be the polarity in the same, because the diodes and your devices cannot conduct in reverse direction. So, you will have typically the current direction in the same manner in this case like typically also. So, that is virtually we call it like a kind of a replacement of your thyristor bridge, but what is the benefit here? In thyristor bridge you are having a reactive power and harmonics. Here you can eliminate the harmonic because you are operating a PWM, and reactive power burden can be also completely eliminated because this current can be maintained in phase with the proper PWM control in the complete cycle of the AC wave. And of course, this is the another circuit where you are using the third leg for reducing the ripple virtually in the output voltage like also. So, coming to of course, the analysis of the single phase bidirectional converter, this is the circuit. If you use it, this is EMI filter. Why it is required? Because this current will be a PWM current here, okay, and here you want continuous current at unity power factor. So, this filter is required because here it is a PWM current and you want here continuous current and sinusoidal current in phase with the voltage. Of course, bidirectional power flow in place of load, then you have to connect a battery here, so that reverse battery, so that power can flow. Voltage direction here can be changed, but current direction cannot be changed because of this inductor like so. So, coming to control part of this, control is quite straightforward here. We have a typically you can call it output voltage we are regulating and we have a reference output voltage. So, we are getting with the controller virtually you can call it the control voltage at the output. This is not only error amplifier, but it is a kind of like a PI controller, PID controller. So, we get amplitude and we are getting virtually the phase form here. So, we are multiplying. So, we are getting this virtually a reference and we are sensing this capacitor voltage. So, we are estimating reference capacitor voltage and we are getting a capacitor voltage here, sense capacitor voltage, and if we maintain the capacitor voltage in a way with the angle which we will discuss of course in next slide. So, we expect that you can have a power factor close to unity like as it is like typically you can see from this phasor diagram. So, with this angle if you maintain the capacitor voltage, in that we can say your voltage virtually in the supply will be in phase with the voltage like also, and how the switching will take place corresponding to that like. So, we like to maintain that voltage in in the typically very close to the reference voltage in the hysteresis, and these are the switching mode which I was mentioning, that you will have these two switches. So, energy flows into that, and typically for mode 2 this like you can call it like a when the other two devices move, but you have in between the another mode where you will have a freewheeling action where I s will be equal to I 0, that is the freewheeling action, and that action is responsible for typically controlling the current in that case like. So, line voltage that and line current are sinusoidally varying. So, we can say this is line voltage, line current like in terms of amplitude and this, and the power we can call it will be VR IR upon 2, where these are the typically you can call it multiply the sign, and that will be average current. So, where S1 S4 are on, S2 off, the net current flows I minus IR flow to the capacitor, and this typically the you can call it capacitor current will be typically of this, and similarly in off period you can call it S1 S4 are on, S2 off. So, this will be the typically the current flowing into the circuit through capacitor, like charges and discharges the capacitor, and you can have a duty cycle in terms of this. So, from where you can have a relation for the duty cycle for maintaining this, and from this you can find out for D max and minimum and maximum duty cycle, and then switching frequency you can have a relation with this, and we can say switching frequency have to be related with in this manner for typically power, and this is the maximum switching frequency which you can have here, and minimum and maximum switching frequency goes in terms of the typically factor of K. And then the voltage, you can call it voltage across the output inductor, is given in terms of your V c into T d minus V o, and V L 2, that during the this expression it can be simplified in terms of your typically in terms of you can keep the value of each term from the other expression, and the impedance of C 1 is much larger than the impedance of L 1 of line. So, V c 1 is approximately equal to the voltage we are assuming the low ripple. So, you can call it V L 2 will be L 2 d I by d 2, and that will be corresponding to, you can call it like a V r I r cos 2 omega t by 2 0, and from this you can find out the ripple current as a function of V L 2 upon I L 2, and this will be corresponding to the function of this. So, this ripple for maximum ripple this will be 1, and from given ripple you can find out the value of the inductor from this relation. Okay, typically. So, you can call it like L 2 will be your V r I r divided by 4 I 0 into omega and I ripple, like. So, inductor value can be there. Once you know the inductor, I mean for giving output voltage ripple, from this relation you can find out the value of capacitor. So, that gives the value of the inductor and capacitor as far as design of converter is concerned, like. And after having a design, you can just clearly see how the typically the input current, which is sinusoidal, can be, and these are the switching function corresponding to that for maintaining sinusoidal voltage also, and this is the voltage and current relation virtually to have a typically you can call it like a input current and input voltage, and this is typically you can call it the output voltage, like. I mean, so, you can have a current in phase with the voltage, I mean here, and of course, this is the you can call it the voltage of the inductor ripple in that case, like. So, now coming to analysis, design and simulation performance of PFC bridgeless buck converter. I mean, this is what we are talking about, like a it is a your MI filter, with that we are putting buck converter, DC-DC buck converter, and from which we are able to control with the power 1, which we discuss it. So, this is with the diode bridge, and this is like a bridgeless. You can see why this is bridgeless. So, we are eliminating this diode bridge up to some extent, and for positive half cycle this buck converter is operating, and for negative half cycle the second converter is operating. So, we call it this bridgeless power factor correction converter, compared to this is with the bridge and this is with the bridgeless also. And coming to this, there are of course many topology of this bridgeless version also of this. So, this is first topology which we have in previous slide, and how the operation is there of bridgeless for positive half cycle. I mean, it really the path is there of this way for on period. When it is off, you will have filling action, and then you have a for negative half cycle. I mean, you have a typically negative half cycle, you charge the capacitor in this fashion, it current flows this, and when you have a switch of this, so this is the filling action through which you operate it. So, you are able to have like a positive half cycle, negative half cycle, the operation of both your you can call it buck DC-DC converter, and you are able to eliminate the diode bridge from here, like. And of course, you can operate in DCM mode. We already discussed what is the benefit of DCM, operating DCM mode. The size of the inductor can be, or boundary condition mode, you can reduce the size of the inductor in that case also. And these are the typical relation, that average voltage is the output voltage, and you can find out the inductor relation, inductor from there, and if you want DCM, then you can have a less than critical inductance, the value from here, and the output capacitor of course can be calculated from the again second harmonic ripple from this, and the load current, output load current, and the voltage ripple at the DC capacitor, like. So, these are the typically kind of design relation corresponding to that. So, after of course, designing and simulating, this is the typical one case study, that supply voltage is 220 RMS, I mean like, and it is a supply current, you can see in phase and almost sinusoidal current. This is the DC link voltage, which have some second harmonic ripple, depends how much in the design is permitted. For 100 volt output, the power level is 800 volt. So, correspond to that, I mean switching frequency is typically your 20 kilohertz. So, you can clearly see the current corresponding to around the 8 ampere. So, that 800 watt is there in the converter, like, and these are the typical other variables like your inductor current, I mean for positive half cycle, inductor current for negative half cycle, then the switch voltage, switch current, and for the first positive half cycle, and for negative half cycle your switch voltage and switch current like. So, that it means by proper control you are able to have typically easily, because it is operating like in almost like your DCM, so you are able to get inherent power factor correction without sensing the input voltage and input current like, and the TID of the current is maintained even less than 5%, order of 3.09%. You can see the current is sinusoidal, and in the previous slide we have seen it was almost like in phase with the supply voltage, having a power factor correction to unity, neither reactive or no harmonics in the input supply current like another. Now, this is another configuration of your bridgeless buck converter, I mean the modification to previous one, I mean where the devices are connected here, and these are the typically the two inductors. I mean like this converter of bridgeless, of course, I mean maybe of course we are connecting load here, but of course if load required 2 midpoint voltage, that also can be attained from this like. So, this is another topology. So, there have been many topology of all these convert configuration win for bridgeless version of it like. So, now coming to this single phase buck improved power quality converter with high frequency transformer isolation, which I already mentioned that we have a many application where you require isolation. The very purpose of the transformer is number one isolation, another is to get many output voltage, multiple output voltage, and then to get a right voltage at the output. So, this is virtually you can call it like a buck forward. This is virtually after the diode bridge we are putting a forward converter, and this forward converter, I mean we are designing typically in DCM mode. So, in DCM mode we have a two energy storage element, one is the output inductor, another is the magnetizing inductance. So, any one of them we can put in DCM, and once we design in DCM, I mean then voltage follower in the sense the your input current will follow the only by voltage control. So, we have a reference voltage, we have feedback voltage, and we have a voltage controller, maybe a PI controller or PID controller, and directly we are comparing it with the your carrier wave to give the switching signal here. So, in this case we are not sensing input voltage, input current, only by design making the current in output inductor discontinuous we are able to get the directly the typically the power factor inherent power factor correction, but this we call it the voltage follower approach. So, only by using single loop which we require regulated output voltage we are able to get even a power factor correction also by design itself like I mean also. So, that is buck forward. Similarly, we can have a buck push pull configuration also. I mean here also this inductor we can design in DCM, or the even the transformer magnetizing we can have a in DCM, and here also of course we are typically you can call it we have only voltage control here. I mean output voltage control, we have a reference feedback and we have a voltage controller, and output of this we are comparing with the high frequency generation, and in this case of course we are switching alternately in push pull configuration of this alternately either this switch or this switch in one pendulum cycle, another pendulum cycle, and this also in voltage follower mode with proper DCM design, it also give inherent power factor correction without sensing input voltage and input current like. But already we discussed it, you can call it the current might be jumping from even in this inductor from 0 to twice once you make the discontinuous mode of conduction like also. Similarly, we have a buck half bridge, I mean in this case also in a half bridge also again we are having only the with the this inductor designing in DCM discontinuous mode or taking this inductor quite low, then we have a feedback only voltage follower in the sense only voltage controller give you power factor correction. So, we have feedback and we have voltage PID control which you compare high frequency sawtooth and give the alternately the signal to these two devices and it give inherent power factor correction. So, these converter of course, forward we use in very low power rating, then we forward with push pull little higher rating, and this also further little higher rating we use it, and finally, for very high power we use the bridge configuration which is here like with again voltage follower. So, again this inductor design in DCM. So, we have a reference voltage and we have a feedback voltage. So, with voltage controller compare with the high frequency, and of course, we give the pulses alternately on one pendulum cycle to these two devices, another half cycle in the other two devices, and it also provide inherent power factor correction because of voltage follower approach. But we have to take a design that at which the switching frequency you are operating, that this inductor current should be typically discontinuous like. And these are of course, the relation for all these four topology, I mean forward buck, push pull buck and half bridge buck and full bridge buck for deciding the inductor value. I mean this is of course, the output voltage relation. This is the of course, inductor for CCM, this is the inductor for DCM. The minimum inductance you have to select less than that, and these are similarly for push pull also, similarly for you have a half bridge also, similarly you have a full bridge also, but output capacitor of course, depends on second harmonic. So, this relations remain the same like. and these are typically like after designing that with that rating of 48 volt and 100 watt, especially for continuous conduction mode. These are the parameters of the circuit like for all these 4 converters and controller gains like because I mean you require the controllers here also, and the voltage ripple how much in voltage, and you can see the TAD is less than 5% in all cases, and these are the and almost like a distortion factor is 0.999, and then power factor is also almost close to unity, and crest factor is also very close to sine wave with the small voltage ripple there. So, this is with the performance with the CCM, and this is typically the I mean corresponding to, you can call it the switch voltage, switch current rating, switch voltage rating, and the power density, of course, cost and other factors responsible for that, like for all these 4 mode. Like the similar exercise is here, it is for DCM with the same output power like a 48 volt and 100 watt, to just give you idea that what is the relative component and gains and all that. So, here also of course, the TAD slightly increases more here, I mean like but still the power factor is not very far from 0.99 or so, and these are of course, the component value corresponding to design for all 4 converter, including the controller gains like also in case of DCM like. And these are the of course, the you can call it the switch current rating, switch voltage rating, power density and transient response, I mean how much overshoot, undershoot are there corresponding to that like. So, this is typically the, you can call it the waveform of supply, input supply current with the TAD of 3 point in CCM for corresponding to the result what we have shown, and this is for push-pull buck topology. This TAD increases slightly more in this case, around 4.47, but is still less than 5%, and this is corresponding to like a half bridge, that I mean the input supply current of 3.88, and this is corresponding to your the bridge configuration. So, this is 2.74% in CCM, and this is the case for in DCM, the TAD slightly increases, I mean this around none, but of course, for low power even the standard allow up to 18% or 20%. So, this is still quite good TAD, and this is for corresponding to your push-pull topology in DCM. In DCM, we have a little higher TAD because we are not sensing input voltage, input current, so we are reducing, but not very inferior performance, and for half bridge it is 7.41 the supply current TAD, and here it is for bridge it is only 7.54. So, even it has been less than 10%, I mean according to standard qualify correspond to that. So, with this now we come to the numerical examples or numerical problems on these converters. So, design a single phase power factor corrected non isolated single switch buck AC/DC converter in discontinuous conduction mode, also known as voltage follower at 20 kilohertz with the following specification of 230 volt, 50 hertz and single phase AC supply, and DC output is 120 volt and 500 watt with the output voltage ripple less than 2%. So, here of course, we have a typically you can call it here voltage follower approach. We are sensing the output voltage, and this is the reference voltage control giving the pulse here. So, it means it is of course, we are putting EMI filter, so that the diode bridge can be a power diode. So, we are putting DCM means this inductor should be in design DCM. So, this is the output voltage relation. We have input voltage from supply voltage. So, we can have a duty cycle calculation for given output voltage of 120 volt, and from output voltage and power we get the output average current. Then we can get equivalent load current from this relation, and we are getting of course, corresponding to 20 kilohertz we are able to get the inductance, I mean that is you can call it the inductance, critical inductance for buck converter. So, that is the typical value of 302 millihenry. Of course, operating in DCM we have to select the value less than that only, I mean like also, and therefore, for discontinuous conduction the inductance should be lesser than, and thus is chosen to 0.25 millihenry, that is 250 microhenry, and the value of the DC link capacitor is calculated corresponding from this relation P upon VO divided by 2 mega. So, putting the value it comes to 0.8 millifarad. So, we select little higher, so that the ripple is always less than that what we select 2%. So, it comes 3 millifarad like. So, coming to second example, design a single phase power factor non isolated single switch buck AC/DC converter in continuous conduction mode operating at 50 kilohertz following the specification of 220 volt 50 hertz single phase AC supply, output voltage 100 and output power 1 kilowatt 1000 watt with the output voltage equal to 2%. So, here we have typically you can call it like again MI filter here, And but in continuous conduction what we are doing, we are just having a voltage loop, and this output voltage controller, we are considering this as a typically amplitude of the current. So, here we have to sense the typically the voltage to give a wave shape and multiply this will be a reference current here at after the diode rectifier. We sense this current, and by comparing the two with the error and comparing with the high frequency, we give the gating signal. So, this is it means in case of CCM we require virtually typically the two more sensor, one current sensor here and one voltage sensor here in addition to the voltage sensor here. And the solution is that output voltage is D times Vn. So, we can have average input voltage after diode rectifier, then we can find out the duty cycle from given output voltage and from this voltage under nominal condition, and then we can have a of course, the load current output current, and from this we can find out equivalent resistance, load resistance, and from we have a considering 20% current, the optimum value of inductance can be calculated from this relation, and to be continuous mode conduction it should be higher than, so we select a little higher than 0.8 millihenry, and the value of capacitor is calculated from typically from this relation, output current divided by 2 omega into delta V, so it comes 8 milli. So, we select the next standard value of 8.8 millifarad like. Coming to third example, design a 300 watt power factor corrected bridgeless buck converter operating in continuous conduction mode to maintain DC link voltage of 100 volt with the percentage ripple of 20% with the input inductor and 4% in the DC capacitor. So, power factor correction converter is to be operated at 220 volt 50 hertz input and switching frequency of 40 kilohertz. Calculate the value of inductor and the DC link capacitor. So, this is what we call it bridgeless version, we discussed already earlier. So, here of course, this inductor current should be continuous. So, this is the average voltage after typically you can call it which are applied here across the converter, and from the input output voltage we can find out the duty cycle, and from this we get the equivalent input current and then the equivalent output load resistance from power and output voltage, and from this we can find out the value of the inductor for given current ripple of 20%. So, it comes 2.06, and the DC link capacitors virtually we are able to get from this again ID upon 2 me. So, from this relation it comes like 1194.26 microfarad. So, coming to example 4, the calculate the value of turns ratio inductor output DC capacitor of a single phase power factor AC forward buck converter in DCM with the high frequency transformer acceleration at 50 kilohertz with the following specification: input voltage is 230 volt 50 hertz and single phase AC supply, and output voltage is 60 volt at 1.2 kilowatt power, and voltage ripple output is typically. So, it is designed virtually in case of discontinuous conduction mode. So, we are only sensing the voltage here output voltage and with the reference voltage with the voltage controller and just giving a gate signal to typically this. So, coming to numerical part of this, with the input supply voltage 230 volt 50 hertz, switching frequency 50 kilohertz, and output voltage 60 volt with the power of 1.2 kilowatt. So, we can find out output load current, that is power divided by current. So, that is a 20 ampere, and we have a ripple voltage of 2%. So, it comes of 1.2 volt, and the rectified output of diode is virtually average of 230, that is a 207 volt. The first we can find out turns ratio. So, from the relation of V output V in D upon V in, we can find out turns ratio may vary in the typically for which the typically the ratio may vary from 0.6 to 3 in the range of, if D we allow to vary 0.45 to 1. So, therefore, the turns ratio is selected 2, and once you have N2 upon N1 2, the duty ratio is calculated as typically like a 0.15 and obtain duty ratio in the range of duty cycle. So, for DCM output inductor we can calculate from critical value. So, from it comes 26.55. So, we have to, therefore, the L0 should be less than this value. So, we can select much lesser than even maybe out of 25 or lesser than that in all cases like. And output capacitor from that same relation I 0 upon 2 omega with the for a given ripple we get 26.53 millifarad like, because we want very small ripple in that case like. So, coming to another example, design a single phase power factor connected AC to DC forward converter in continuous conduction mode, operation with the high frequency transformer isolation operating at 50 kilowatt with the following specification of input voltage 160 volt and 50 hertz and single phase AC supply and output voltage 75 volt and 1.5 kilowatt output with the output ripple less than 5% and output inductor current also less than 5%. So, this inductor is also having less than 5% and this capacitor voltage is also less than 5%. So, these are the data input voltage 160 volt RMS with the switching frequency 50 kilowatts, output voltage 75 volt with the 1.5 kilowatt power. So, we can find out typically the output current load current of 20 ampere. So, for a given ripple voltage once we know the output voltage we can find out typically the voltage ripple is 3.75 and ripple current is corresponding to around 1 ampere. So, rectified output of diode rectifier is 0.9 into 160 that is 144 and the turns ratio from this relation we can find out may vary from this range. So, we can find out typically for this duty cycle range we can select 2 and from this we can find out the duty cycle typically order of 0.26 and obtain duty ratio in the range of defined. So, for CCM operation the minimum inductance value we are finding critical value from this. So, it should be more than that, then only we can say that will be operating in continuous conduction mode, that is the typical value in which and the design of output capacitor from the voltage ripple we can find out typically from here from power divided by voltage that is the current and multiply to. So, it comes 8.5 millifarad. Like coming to sixth example, design a single phase power factor connected AC to DC push pull buck converter in continuous conduction mode with a high frequency transformer isolation operating at 50 kilohertz with the following specification of input voltage 230 volt 50 hertz and single phase AC supply, output voltage 120 volt and power is 1.5 kilowatt with the output voltage less than 2% and output in current is 5% like. So, in this case given a voltage input 230 volt, switching frequency 50 kilowatt, output voltage 120 volt and power is 1500 watt. So, output current is 12.5 ampere and 5% of is 0.625 and output voltage ripple of 2% is the 2.4 volt. So, rectified input voltage 0.9 into 230 that is a 207 and the turns ratio from typically of this relation we have called 2 open to Vane. So, N2 may vary within the range of this. So, we can have a duty cycle between point. So, therefore, we can select in between 2 and from this we can find out duty ratio and obtain duty ratio. Now, from this duty ratio and turns ratio we can find out the minimum inductance value for CCM, that is for critical inductance. So, we have to select higher than this. So, that comes 1.5 millihenry and from design of capacitor this value for a given ripple voltage we can find out 8.3 millifarad like. So, coming to example 7, design a single phase power factor corrected push pull buck converter in DCM with a high frequency transformer isolation operating 50 kilohertz and input voltage 230 volt 50 hertz, single phase AC supply of 48 volt and 500 watt with the output voltage ripple less than 2%. Since it is DCM, so we have to design this inductor in DCM conduction mode. So, given data that input voltage 230 volt, switching frequency 50 kilohertz, output voltage 48 volt and typically 500 watt and we can find out output current from P upon V output power divided by output voltage. So, 10.4 and voltage ripple of 2% of 48 volt. So, it comes 0.96 and rectified output input is your 0.9 times 230 that is 2. So, from this relation of VO equal to 2 Vin into D upon we have to find out turns ratio may vary from this to this. So, if D allowed to change 0.45 to 1, therefore, the turns ratio is selected typically 0.65. So, once you have 0.5, so you can find out duty ratio 0.18 and obtain duty ratio is in the range of selected. So, from the relation of this inductance for critical condition, we can find out the critical condition of 14.8 microfarad and microhenry. So, therefore, the value of output inductance should be less than to ensure and the design of DC capacitor of course, from this relation we can have 17.3 millifarad like. So, design a 8th example, design a single phase power factor corrected AC DC half bridge buck converter in DCM with the voltage follower approach with high frequency transformer isolation operating at 50 kilohertz with the following specification of VI 230 volt 50 hertz, single phase AC supply with the output voltage of 24 volt with the power 200 watt, output voltage ripple is less than 5%. So, here it again DCM. So, we are designing this inductor in DCM with the power control So, given here that input voltage 230 volt at 50 kilohertz, output voltage 24 volt and power is 200 watt, and output current is typically P upon V O, so it comes 8.3 ampere, and output voltage ripple is 2% means of 24 is 7.2 volt, and rectified output is 20, average voltage is 207 volt after the diode rectifier. So, for getting a turns ratio, V equal to V in D upon N21 upon N1. So, this may vary from 0.25 to 1.2 in the if D varies from 0.45 to 1. Therefore, the turns ratio is selected 0.65, and getting this, so we can calculate the duty ratio. This duty ratio is in the range of typically the what we already have for proper design, and the design of output inductor for critical value, I mean for DCM is putting the value in this case, so it comes 9.2. So, we are to select less than that, so it comes 5 microhenry to ensure DCM, and design of DC link capacitor from this relation it comes 11 millifarad like. Coming to example 9, design a single phase power factor full bridge buck converter in discontinuous mode. It means inductor is designed in DCM with a high frequency transformer isolation operating at 50 kilohertz with the following specification: input voltage 220 volt 50 hertz, and the single phase supply of output voltage 48 volt with the 800 watt with the output ripple less than 2%. I mean, so these are typically in DCM, so you require only voltage loop. And coming to numerical part, so input voltage 220 volt at 50 kilohertz design, output voltage 48 volt and output power 800 watt. So, we can find out output current P0 upon V0, so it comes 16.7 ampere, and the output voltage ripple 2% of output voltage, it comes 0.96 volt, and the rectified output average voltage is 0.9 to 20, so it comes like a 198 volt, and the turns ratio from the relation of V0 upon to N, the turns ratio may vary between 0.25 to 1.2 if D is selected between 0.5 to 1, therefore, turns ratio is selected 0.65. Once you select turns ratio point, D is calculated 0.19 and obtained duty ratio is in the duty ratio range. So, from for DCM we can calculate the value of limiting inductor or critical inductance from output load resistance. So, it comes like 9 microhenry, so we can select the output inductor selected 5 much lesser than that, that is 5 microhenry for DCM operation in all operating condition, and the output capacitor, I mean like the filter capacitor is selected from power voltage ripple, so it comes 27.6 millifarad like. So, coming to the 10th example, design a single phase power factor bridge boost buck converter in continuous conduction mode with high frequency transformer isolation at 50 kilohertz following specification with the 220 volt 50 hertz single phase supply. Output voltage is 72 volt and power is 1500 watt with the output voltage ripple less than 5%, and output inductor current is also less than 5% of this typically. So, coming to numerical part of it, so output voltage input voltage 220 volt at design at 50 kilohertz transformer, and output voltage is 72 volt with 1500 watt output. The output current is calculated from output power and output voltage 20.8, and output voltage ripple from output voltage and 5% of ripple 3.6, and output inductor current 1.04, and the input average voltage comes out your 0.9 into 220 is 198, and the turns ratio from the relation V upon 2 Vin from this turns may vary from 0.4 to 1.82 if we take a duty cycle 0.45 to 1, therefore, turns ratio is selected 0.65, and for this the duty ratio comes for a given condition 0.28, which is in the typical range, and the inductance for critical inductance virtually comes from the relation 0.3. So, we have to select higher than that for CCM 0.5 to ensure CCM for all operating condition, and the design of DC link capacitor, filter capacitor calculated from power and voltage ripple. So, it comes 9.2 millifarad. So, coming to summarize this buck converter, improved power quality buck converter, the operational analysis of various type of single phase unidirectional bidirectional buck converters are discussed with their design procedure and control approach. The bridgeless buck converter ensure minimum conducting device with switching cycle operation and require minimum component count, and a number of practical examples of buck improved power quality converters are given with the view of proper design exposure while considering the improved power quality performance, and these are the references we have covered here. Thank you very much.